Welcome back, everybody. Let's start next lecture in Perception in Robotics. Today's lecture is going to be on localization as well, right? But before getting here, let's do a brief summary of what we did Thursday, right? So we introduced now this problem on localization. We talk a lot about distributions, Gaussians, and base filter especially, and the Kalman filter. But last day, we start talking about localization. So why is this problem particularly different from just general state estimation? Well, what we said is that there's going to be a map of known landmarks, right? So remember, these landmarks are just positions in this case, we started with two-dimensional positions, but these correspond to salient features, right, in any environment, like corners, doors, whatever you want to describe as landmark. So we have now a set of them, right, each of them with X and Y coordinates. Right, and for us, this is our abstraction of map so far in this first introduction to localization, right, all these different landmarks that are there. And then what we argue is that the localization problem, if we take enough considerations, then becomes a state estimation problem, right? And then the belief, as we were always describing before on the base filter and Kalman filter, becomes this. We want to estimate our current state, given all the actions that we have executed, all the observations, and now also given that we know the positions, right, of all these landmarks. Basically, we know the map. So given these three things, now the only new one is map, right? New. So we can still use the other techniques that we explained, like imagine we have a nonlinear observation function or transition function, then we can use the extended Kalman filter, right? We said that this is the first approach. Today we are going to describe a slightly different approach, right, but still based on the base filter. So I'm going to go into details now. And how is this possible? Right? How is it possible that we can localize ourselves just doing the previous state estimation techniques? Right? Basically, how is it possible that we can condition with respect to the map? We had to do a strong assumption, right? And it's the following. So we assume, I'm writing here for now because later we'll see what happens. Oops, it died. Hold on. Okay, give me a minute. Oops. Okay. Okay, so this is our assumption for now, that landmarks and observations, these correspondences are known, right? And we wrote this the following way, right? So we have this new variable, C, which is the correspondences, and then for each observation, for each set, right, this corresponds to the index of a landmark. In this case, indexes of landmarks are J, right? Or if you prefer, we can use this, maybe a little more clear, right? From observations, each observation, right? It's the unique association of one landmark, right? So this solves part of our problems, right? This is basically known correspondences. And well, this is introduction. We will discuss later what happens when we don't have these correspondences, right? What things we can do. And yeah, so with this, you already you have all the material to start with problem set 2. Has someone already started with this? No? A little? At least open? Play around if you see things moving? Set the virtual environment? No? You're waiting for the weekend? Okay. We will confirm, but I think Monday is holiday here, or there's definitely not class. Is that correct? So we might change a little the deadline, maybe instead of Sunday to be Monday. Okay, I will confirm this. So far, it's what Canvas said, not me, right? But if someone comes and say, look, I have started doing this and I need one more day, maybe we will move it, right? But start doing it. Okay, I also forgot last day to talk about a different kind of transformation. So if the EKF is the first order linearization of the base filter, there's another transformation that I'm not going to explain in detail, but we did last year, and actually that was part of problem set 2. For you, I think now it's just like enough to know a little about this, which is the on-send transformation or sigma points, right? So with this, this basically gives rise to unsend Kalman filter, right? And this is based again on sigma points or unsended transformation. Okay, just for you to get an idea, this is something in between linearizing, which has problems if you are not really close to the optimum, right, of linearization. We said, what did we say? That our linearization point, it's always mean, right? This is the best guess we have. But sometimes the error between, the error between the mean on our estimation and the real value might be considerable. That's why we discussed last day what happens when we update, like things not on batch updates, right? Do you remember? But incrementally, so we have one observations, we improve a little, we correct the estimate, and then we add more observations, right? We discuss what's the advantage between a batch update on all your observations versus an iterative updating, right, of the observations. So this is another way of preventing this problem, right? The unsent. Just very, very briefly, I'm going to say that it's still based on a unimodal distribution. So what we are going to be doing here is we have a normal distribution, right? From this normal distribution, we are going to select a small set of sigma points, right? Let me just write them like this, right? So this is our prior. We get here some points, and this is a small set. In general, it's going to be the dimensionality 2 times plus 1. So these points are strategically, let's say, not sampled, but just obtained from the prior distribution, which we assume it's Gaussian. And then what we do is we simply do whatever nonlinear function we have for each of these points. So if you remember, the difference when we apply the extended Kalman filter is we just do this once for the mean, right? So we just apply this nonlinear function to the mean, and then we were doing covariance propagation. Now it's a little different. Now we propagate this for all particles. So imagine here we have a 2-dimensional one, right? Let's say that I'm just drawing these 5 particles, and this is an isocontour of your 2-dimensional, right? So this is particle 1. Now the beauty of this is how to select these particles to be actually representative of your distribution, right? Okay, and then for each of them, you apply H. So what's the advantage of this? That it's not just the mean, but you will be transforming, and maybe as a result you get something that is not even symmetric. It doesn't resemble like an ellipsoid. It might be anything. I mean, maybe this comes here for whatever reason. And then what the sigma points do is they have a property such that once you have these points propagated, you can estimate a new posterior just based on these points, right? So basically, well, it's a formula, but then it's going to be Gaussian again. This is the difference. So you get these points, and there's a formula that will get you, again, a Gaussian distribution. The advantage of this is that we are not doing just covariance transformation, but just non-linear transformation of each of the points. And then you still get like well, with these points, then you can build your estimation to be Gaussian, but this is going to be a little closer to reality if you were doing like the proper nonlinear. Okay, so hold on. This is just for you to know. Today I'm going to discuss a little more on how are we doing all these particles. Yes? Can you repeat it? Yes. The problem is errors on linearization. So if you have errors on linearization because it doesn't resemble like your linearization point, maybe it's far from optimum, or you have a large range of inputs, and then you are going to have like error and you know about it, maybe this will help, right? No, that's the thing. So there's notes on this, on the unsensed Kalman transformation and sigma points on Canvas, right? So I updated like extra material for this. I'm not going to explain it in detail. There's always explanation in probabilistic robotics, but the trick of this is that you don't need a large number of samples. I'm going to explain today a particle filter, which is based on this brute force approach of having a lot of samples, and this will give you any representation for your distribution. This is just based on, let's say in this case, dimension is 2, so we have 4 plus 1. Just with 5 particles or with 5 sigma points, you can still have like nice statistical properties, right? Okay, so again, I'm not going to ask you to implement things on this. I'm not going to ask you things about sigma points on sensed transformations in the exam, but it's for you to know. Okay, so now let's move to, you will see it's an approach in between the unsensed transformation. Let's move to the brute force and non-parametric solution for localization, which is based on particle filters. Okay, so today I'm going to explain particle filters and how to apply this to the localization problem. Okay, so if you remember, we defined the base filter, right? And we obtained these equations, these iterative equations, and that was very attractive, right? Because now with a very compact, just 2 formulas, or if you want, you can put this just in 1 line, we could be representing like any state estimation given some properties. We know that we need the Markovian property, right? And well, that was it. Then this holds for any distribution. So we also discussed that in practice this is not very useful because not many distributions after this marginalization and after conditioning we know exactly what they are, right? But this compact and I think very intuitive formulation, it's still, let's say that can still be used like outside Gaussians, right? It's simply like very, very expensive. But today I'm going to explain like another method just to, another method derived from the base filter that you will see that it is still useful. It has some disadvantages, but the idea is if this is true for any distribution, then let's use any distribution. Okay, so again, base filter, right? And what we have discussed so far is that this is excellent if we have Gaussian priors and all our likelihood functions are Gaussian, right? So for Gaussians, this is straightforward. And let's say that this gives rise to the Gaussian filters family, right? So here inside we have Kalman filter, we have extended Kalman filter, and now this new approach that I just briefly introduced, right? There's no need for you to know, but it's based on the same principle. So we have the unsent transformation, and basically we'll have exactly the same, well, with some particularities, the same equations that we had in the Kalman filter, right? So this is for linear, and this is nonlinear, right? And this is the same. Okay, so this is what we have explained. Lecture 6, if you remember. Lecture 4 also. All the time we were just deriving this from this equation. So this is very useful. Now, maybe some of you have this question, what happens when we have like other kind of distributions, any kind of distribution, right? So for this, there's still a family of methods, right, which are basically non-parametric that are still useful for some of these problems, not all of them, right? And basically, the one that we are going to explain here is the particle filter. So just to have an idea of what we are going to be doing today, it can be summarized in this equation. We are just going to we are going to do all the definitions, and then we are going to justify how to apply basically like sets of particles to approximate all these distributions, right? And at the end, we are just going to work with that large set of particles which are going to be approximating all these equations, right? So it's always the same principle. Behind, there's the base filter, right? These two equations, but instead of saying now, okay, for Gaussians, we know that this is very efficient. We can calculate this marginalization and this conditioning, but for other things, we don't know. It's actually hard. With non-parametric methods, what you do is instead of trying to get like a closed form or a numerical form, you just have like a bunch of samples that give you a statistical representation of the same beliefs and the same likelihood functions. In this case, this is the transition model, and this is the observation model. Okay, so this is kind of roadmap for today. We are just going to be talking about particles, but this all comes from base filter. Okay, what is a potential advantage of using particle filters? I think we already discussed on this. Imagine you have this sort of distribution, right? So maybe the mean of this is around here, right? This is the mean of this distribution. I don't know, I'm just making this up. So how is this going to look like the moment we start linearizing, we start like proposing a estimation, a Gaussian estimation of this? It's going to look bad, right? So basically, you can imagine something like this, right? Basically, we'll have our mode in between the two modes. So this has some disadvantages, but now imagine that we can have any kind of distribution, right? And we are going to describe now exactly how this is done. But for this kind of multimodal cases, this is going to be an advantage. So these kind of distributions, again, for Gaussian and linear cases, we are going to be in trouble. There's always going to be a unimodal solution. And maybe this is bad. Maybe each of these peaks in this distribution are telling you that there's like a wall in between, and you can be either in one side or the other, right? And then if you linearize, you could be basically in the middle of them. Yes? No, because if you do that, yes, you can do that, but then there's a problem, and if you remember in this, I'm just going to motivate this. If you remember the example of the doors, when you had a sum of Gaussians, what you get is that every time that you propagate, and every time especially that you add observations and you have a correction, you basically have a one-to-all updates, right? So basically your two modes are just going to be exploding. You are going to have many more modes. So either you branch some of your Gaussians that are not contributing, or you do any other kind of trick, but if you treat this like exhaustively, all your modes, I mean all your sums in your Gaussian, this is going to be out of control very quickly. Right, so it might be two, but then maybe after some steps, depending on the observation, it's going to be much more. So yeah, I guess you can rework your formulas just to work with max or of sum of Gaussians, but if you just treat this properly, you are going to have like an explosion, right? So it's a good point, by the way. At the end, the base filter, it's a very powerful approach, right? So we have the formulas, it works for any distribution, we are not doing any strong assumption. So why don't we use like for multimodal cases like this, right? Could be. I'm sure that there's publications on this. I didn't check, but yeah. Okay, so we are just gonna talk today about a different approach for doing this, right? Instead of just still making use of Gaussians, we are gonna use a total different thing. And well, basically this starts just by describing like these distributions as particle sets drawn from this distribution, right? And if we have enough of these particles, this can be representative, right? So, oops. Let's start just defining this, the particle set. And now you will see more clear what I mean by this non-parametric representation. So I'm going to have this x capital, right? And here we are going to have this. We have like whatever state variable it is, right, for, let's say, the first particle. And then we also have a weight, right? So this pair, weight, I'm going to explain later exactly why we need it. Well, depends on how you are using. You might not need it, right? Just have draw samples and you assume that weights are equal for all of them. But in this case, you will see that actually this will help us to have a better algorithm. And then, well, basically we have m particles, right? Okay. So just to give an example on the previous two-modal thing, now what we'll have on this distribution is we don't have any first-order moment or second-order moment, no covariance, nothing. We just have a bunch of particles. Imagine that this is well distributed. Right? And at the end, if we have enough of them by the law of large numbers, basically these will converge exactly to the distribution, right? So if you sample enough of these particles from this distribution, this is what I'm writing here, at the end you will have like the representation, I mean this distribution that we are looking for. So it's very powerful, it's very simple, it's not very efficient. But the idea is clear, right? Forget about if distributions now were just described by a mean and a Gaussian, now our distributions is just going to be this particle set. Okay? Yes? No. You should be drawing them independently from this distribution. This problem that I explained of choosing them, this is the sigma point algorithm, right? So if you choose them, but you need to know some things about your distribution. In this case, sigma points assume that you have a Gaussian distribution, or at least unimodal. For this, you just draw them. Anything, it can be anything. There could be a mode here, and you still, if you have enough samples, you will sample, right? So this is very powerful. That's why it's called non-parametric. You don't assume anything. You just put there a bunch of samples, and then they will be representing this distribution. Okay. Any other question? No. Okay, well, so problem set one, you were already doing a little bit of this, right? So I was asking you, well, you have this Gaussian distribution, and then you draw samples, you drew samples, and then you were doing covariance, well, sample mean and sample covariance, right? And it was kind of matching. In this case, so you just keep that number of samples. You don't assume that then you will need to do a sample covariance, right? Because that must be a Gaussian. No, it can be anything, but you will keep the whole set. Okay. Yep. That's a good point. You will see in a moment. So still, we need some priors, right? But what's going to be different is that once you have a prior and you let the algorithm run, remember, this is an iterative process, multiple modes can appear, right? So even if you start just with, let's say, a Gaussian prior, which is unimodal and center, depending on your observation functions and depending on your transition functions, maybe different modes will appear. This is iterative, so you might start with a prior that is known and has a formula, but then later the distributions that you're representing are any kind, right? All of them can be represented. No, you store the whole set of the set of points of particles. This will be your, and then here, from here, you can do sample mean and sample covariance if you want. No, you store full row set of all samples, right? This is what I'm writing here. That's why you are not assuming anything about it, right? So this is the particle set, all samples. You store all of them. That's what I was saying, that this is not the most efficient thing. But still, with this, you can capture any kind of distribution. Okay, so for now, let's not worry a little too much about priors. Multimodals will appear anyway, or not. And let's see this in action. Okay, so, well, here, this is what I'm writing. This is drawn from this distribution, right? Either if it's drawn or we'll see that this is an iterative process. We'll see, but basically we have now like this set, and then the same goes for these weights, right? And these weights are just going to be the evaluation of these particles, right, according to some likelihood function. Okay, so these are the components of our particle set, right? This is point, and this is weights. These are actually called importance factors, and I will explain them properly later. You have a question? Yeah, please. Yes. Exactly. So so are you asking how can we sample from this distribution? It's kind of the problem of the prior, right, that your colleague asked. So for now, let's assume that you have drawn these samples, but you didn't sample them. You have just these samples, right? And this is what it's going to be representing your distribution, this set of samples. Either if you draw them with your call to some function, or you already had them after iterative transformations, we will see. But basically, it must not, I mean, you don't have to have like full access to this distribution. You will just have all these particles that are drawn from this distribution. Maybe not by you. Okay. This is going to be probably half of our class. We are going to be explaining what they are for, right? So what is the vanilla, or let's say initial description of this? Your factors are equal, right? So you draw from a known distribution, right? And then you want to have your particle set to be approximating that distribution. So because you know everything, all your weights are going to be equal, right? So this is the standard way of approximating things numerically if you want to do this with particles, right? But in this case, you have direct access to drawing them. You have direct access to some distribution. We'll see that these factors are going to be useful the moment that we start transforming, right, our particles. But just keep them in mind. I mean, you will see more clearly what they are important for. If you want, now you can say that they are equal. But we are still maintaining them on the set. You had a question? Yeah, please. Yeah, exactly. So I'm just here like saying that we'll have like a likelihood function. I'm just advancing a little material. And basically the weights of these are going to be depending on how likely these states are, right? But this is a new distribution. You might not have direct access to this, so you can just have observations, right, which sometimes are indirect observations. So it's a subtle point. I will explain later with more detail exactly what these weights are. But what we want is that on the particle set, we are going to have pairs of states and weights, right? Okay, so I think I already said, but what were then the weights on problem set 1? When you were doing sampling over your distribution, which weights were you using? Even weights, yeah, exactly. So that's what I said before, that this is the first initial approach. You just consider them equal, and this is the standard way of sampling from a distribution. So it's just going to be this extra component, but it's very similar. The idea is the same. Okay, so I'm going to write here the algorithm, and then we are going to go function by function, and you will see clearly where everything comes from, right? But compared to EKF localization, or let's say just EKF, particle filter is very compact, right? It's just 5 lines, 6 lines. So what we need is our prior, right? This is always the same for all filtering algorithms. Now, in this case, our prior is a set of particles, right? What else do we need? We have an observation, and then we have an action, right? So this is all we need. The output, what is it going to be? It's going to be another set of particles, right? So you will see. Okay, so basically we iterate for all of these particles, right? What we do is we are going to sample. No. We are going to sample our motion model. So still remember that there was uncertainty on our motion model. We need to execute actions, and sometimes this will give different results for the exact same action and the exact state. So we need also to capture this. Okay. Okay. So this basically is what is related to propagation. So our large formula with the with the marginalization simply goes away, and we are going to be executing this. So I'm going to explain you why this holds and why there's like probabilistic reasons just to do it this way. Okay, so this is propagation. Okay, yes. This one. No, this is a particle. This is not the set of particles. So let me rewrite it. Let me rewrite it in a second. Yeah, but it's important. So this is small x. The set is capital. Yes. This one? Yeah. Okay, so now it's correct. We are just drawing this, and the same, it's going to happen for weights, right? So for each weight, we are going to have this nice and compact formula. We are going to see later exactly what it means. And then we are going to create our, oops. This is set of particles. I'm just putting here a bar because there's going to be a very important last step, which again we are going to discuss later. And basically what we do here is we just do the aggregation, right, of all these new particles that we have obtained. So this will correspond to correction. We are just adding all particles that we are propagating. Right, so far I'm removing a lot of terms compared to the previous Kalman filter, right? So if you remember here, conditioning was also like including many other things, but just with this weight, it's going to be enough for us, right? And we'll see later why. And then there's a last step, so we close for here, right? And then our posterior, this is going to be the output of the algorithm. It's going to be this. We need to resample this set of particles, right? So we are going to resample this. The reasons, again, are going to be explained later. If you just do like a mathematical derivation of all these terms, this is totally fine until you get here. Everything is correct, but it doesn't work. And it was not until 93, right? And I think you have this paper in readings at Canvas, if you want, right? Paper from Gordon that was discussing on state estimation with particle sets that he basically emphasized on the importance of resampling, right? So I'm going to explain today a couple of strategies, but remember, the math until here works. This is totally correct. You will have a posterior that is exactly what you are looking for, propagation and correction, right? But it doesn't work in practice because, yeah. What is the what? This. So what you are doing is you are sampling, and this is your motion model, right? You are sampling a new state given an action, and this action is common for everyone, and given your previous particle, right? So that means that even if you had like the same point here, you are still considering different actions, right? So if you remember when we were talking about the transition function, there was no, it was epsilon, right? So at each instant of time, your transition function right? Your transition function nonlinear, it was added. We needed to add like noise, in this case in the state space, right? So this is what we are accounting for, this epsilon here. We need to consider this uncertainty as well. If you were just doing this, this will be a deterministic function. You cannot do this with a particle, right? Because this is just an instantiation. This is a result of drawing from a sample. If you do that, that's not a distribution. So how we add more noise into the model? Just we draw this propagation, and then the noise is going to be depending on the motion, as we describe on the transition function. Okay, so yep. No, there's no linearization at all. Forget about linearization. This is the beauty of this method. There's no linearization, there's no assumption of Gaussianity, there's no unimodal distributions. It can be anything, as long as you have enough samples. Yeah, I get it. So yes, it's not really an assumption. You need to propose a transition function. We have discussed how to obtain transition functions, right? So in this case, yes, this is one is for obtaining this, you will be using the linearized first model that we explained, right? But in terms of linearizing with respect to the state, there's no mean here, there's no covariance, we don't need this. We only need to propose any kind of distribution, any likelihood function that relates actions and previous state, you execute this action, and then whatever it's going to be as output, right? So this could be any distribution, right? You could sample from that distribution as well. This is what we explained. So this is lecture 5, but you could be using anything. Right, doesn't prevent you. I mean, the algorithm is very flexible. Okay, good point. The same happens here. So observation function can be anything. Okay, so I was talking about this reference. You have this in Canvas if you want to take a look. Right, there's a second reading also on the particle filter, which is the final result of this class. You can also take a look at that. But basically, this is the basically this was stating the importance of resampling. Okay, you have a question? Minor. No. So what you do is you are going to be selecting from your set of particles a new subset of particles. It might be the same number of particles, it might be other ones, but basically the random variable that you are considering here is not x by itself. You just need to select some of these particles, right? No, you just change the distribution of this population. And we are going to discuss later why. If No. The number of particles, it's always constant, right? But then we are going to see like strategies to just select particles. You might repeat some of these particles, right? But by doing this, you are ensuring like there are like very nice statistical properties on this. If you don't resample, then I'm going to explain later what is the problem of this. With infinite number of samples, you don't have any problem. That's what I was saying, that mathematically this is correct. But just for the resample, let's say that we are selecting among this set of particles, we are selecting the same number, right? But exactly, with repetitions. Yes. Maybe, well, I have two algorithms for resampling. You will see later, right? I don't think so, but yes. It will not be Gaussian. We will not, on resampling, it's not that we are going to rebuild this to be Gaussian. No, no, no. Resampling is, that's what I was a little hesitating on the random variable that we are selecting. We just treat particles, and then we are going to be selecting the most interesting particles for our problem, with repetition until we get the same number, but with nicer statistical properties. So think about it. I'm going to give, I will explain later this well, right? But you have this thing. You have these particles. So the idea is that you don't want to keep like particles that are meaningless, like on the tails. Well, this is not. But actually you want to keep like your set of particles like significant with respect to your estimation problem. So that means that maybe these particles are a little more interesting than whatever is here on the tail, right? I will explain later more properly, but this is just the algorithm. As you can see, it's very, very compact. There's going to be a propagation, there's going to be a correction, this is just aggregation, and then this little thing on resampling that was actually crucial, because before that, the algorithms like this were not working properly. Okay, so then let's go. We are going to start here, and well, we are going to do like each of these lines. Okay, so I'm gonna, to start with the first line on the propagation, I need to reformulate slightly the base filter. And in this case, I'm not gonna assume any Markovian properties, but this is for full states. Okay, so this means the following. Now, instead of having x of t, right, last time step that we want to estimate, we are going to estimate all of them, right, from origin of times to the current time, right? So what is this exactly? We are going to have this joint distribution. Imagine you have all your states here, not just the final one, but all of them from 0 to t. And then we are going to condition this, same as before, by all our actions and all our observations. Okay? And, well, remember that particles are always going to be the same. So in this case, what are particles? Right? So each particle, it's going to be basically a sequence of the states from time 0. Right? We are going to have, this is the same particle. We are going to have a state for time 0, for time 1. We are going to have basically on our particles, the dimensionality is just going to grow from 0 to time t. Right? So this is going to be our new redefinition of particles if we want to consider full states. Okay, so sequence of samples. Okay, this is just, well, a mathematical definition that we do at the beginning, so such that then later our base filter it's going to be like simplified. Right, but for now, let's assume this. We have this long chain of states, right? Each of them is going to be a particle. So if we write this belief, it's going to look like this. I'm just applying here Bayes' theorem, right? We are going to calculate this with respect to the last observation. Then observations means that we don't have until time t, right? We are just, this set of observations, what we are doing is changing one of, the last one, right? And then we are going to be conditioning against all the other things, and then we have all actions. Yep. And then what else do we need? well, basically then we need our prior on T, right? In this case, Z T minus 1. And then all actions. Okay, so this is Bayes theorem from this one, right? You can do it later if you want. Then I'm going to apply again Bayes and Markovian property. So, well, yes, we are going to be using it a little, but you will see that not a lot. So this first term becomes like this. You know, I'm just going to write capital U to be all U's from 1 to T. And so what I'm doing is, here this is Markov. And here I'm doing Bayes again. Right? So, no, Bayes, no, actually this is the product rule. Oh, okay. Oh no. I cannot write it this way. Okay, so. Okay, so this depends on all the previous states, all the previous actions, and all the previous observations except the current one. And then finally, what we got here, after doing the it's this condition. At the end, this derivation, it's always the same. You are always looking for a recursive thing, right? So we have now our recursive thing. Right? Yes. Here. Here. Yes. So if you remember the graphical model that I was proposing, the action was already taken into account because we were already estimating this xt, right? So as we were defining, just with the current state, you can define a likelihood function. We never proposed a likelihood function on the observations that depends on the previous state plus action, right? That this was a 2 steps. First, you do the, let's say, a propagation. That means previously this was the marginalization, right? And after you get this, then you added the observation. So this variable is already including your previous state and your action, right? I'm just here like doing some abuse of notation, but this will be like the Markovian properties in the particular case for observations, right? Just with the state, your current state, this is enough to describe your full distribution. It's conditionally independent of whatever you have executed before, right? Once you have this estimate. Yep.
Here we have Markovian property for the observations, but no Markovian property for the states.
Well, you can always use the Markovian property if you want, or you can leave it out if you don't want. In this case, it's not going to be convenient because you see this. We didn't make use of the Markovian property, so we have the full set of sequences. But actually, this is the belief of xt minus 1, right? So we have just get a recursive form now. And now we are going to see that actually here, in all this, we can use the Markovian property. So it's simply on this derivation, it's when to choose to apply this or not. Okay. So far it's very similar to what we already obtained. There's going to be a recursive form depending on the previous belief, right? This is likelihood function as we had from the observations. Here, yeah, we apply Markov. right? So we do have this. And then, as I said, this is just going to be belief of xt minus 1. Right? So this is very, very similar to the approach that we had before. Now there's no marginalization. It's because we are considering the full state, right? So it has some advantages, but we see that if we maintain the full state here, belief is slightly different. Actually, this belief is from 0 to, let me write it correctly. From 0 to t minus 1. So it's not exactly the belief that we had before, right? Here we're including all the previous states. Okay, so now we have a filter, right? We have a filter that it's simply, we have changed like some subindexes, but it's the same idea. Right, and we are going to see that we actually don't need to have all the previous, I mean, our points are not going to be the full sequence of states, right? But it's going to simplify a little, because the important thing is that we have this recursive form. Okay. And then real belief is this. Okay, so it's slightly different if you want to redo this derivation at home, right? But it's going to be very convenient because some of these terms have already appeared in the filter, right, as I described before, right? And we are not making up anything. And the only slightly the only slight difference with respect to before, it's going to be this belief, right? This belief now is including like full state, but if we can represent this with a set of particles, this is going to be enough, right? Okay, so yeah, we go here, and then we go here iteratively. Okay, let's do a short break, and I'm going to explain now how we propagate things. So I think now we have like clear definition of what we want, right? It's this new form derived from base filter, and I'm going to explain exactly from this part exactly why we were obtaining that and what does this mean, and you will see this much more clear. Okay, so 5 minutes. Be back. Okay. Let's get back. There were like a lot of questions. So some of them I think it's relevant. I'm just going to share it. Basically, they were asking, but we have already derived the base filter, right? So what is different? The difference is here. We are calculating the belief of the full state, right, from time 0 to time t. So this makes the problem slightly different. Before, it was just the current time, and that's why we had integral, right? So with this new kind of approach, the base filter with this full state version become a little different, right? It's going to be better for particles, but probably it's not as good if you have like Gaussians. Okay, so basically, what are we going to do now? Let's define this derivation. Right? And then let me write it like this way. This is a particle here at time m. Right? How are we going to obtain this particle? I said that we are going to have a motion model or a transition function that is generating this, this motion model. Right? We have the previous particle, and then we have an action. Right? We know that, well, basically, this is given. This is given. This is good because no longer, That's the other reason. We cannot really do here integration because this is not going to be we don't have the distribution for that. We only have a lot of samples, right? So that's how we are going to be approximating this. What we can say is that this motion model is a probabilistic one. It introduces noise, and if you have this distribution given the previous state and an action, it's going to generate like different results. So I'm going to write here an example of this. Imagine we have this two-dimensional world where we have like some samples, right? These are our, well, this is our particle set at t minus 1, right? And now imagine that, well, we just have, for each of these samples, we are going to be executing we are going to be sampling what is this propagation state, right? So in this case, we are going to be executing the action, right? For this, I don't know, action might be, here I was writing actions to be 0, minus 1. So imagine all these two-dimensional points, you are just subtracting y 1, right? So all of them should go down. Now, the starting point is different, right? So this is what this conditioning means. We start with some sample, and then we add some noise. Imagine that we have this sample repeated, right? So maybe it's here, and then the next result, it's going to be this, right? So this is ut, and then this distribution, right? So each of these initial conditions, the state and the action executed, are actually a distribution, right? Lecture 5, how we obtain this distribution. But basically, this is the model of this, the system that you are using. A car with wheels, some flying thing, a point, whatever, right? Okay, and the same happens for each of the particles. So, yes, this is going to be constant for all of them, but the initial state, it's not. And then still, even if you had the same conditioning variables, you can have different outcomes, right? So that was another question, right? Are we going to do this for every particle? Yes. So we are going to, oops. Yeah. So we are going to be propagating, in this case, oops, G for each particle. So that's M times. Right? So for each of them, we are going to have a transition. This can be very complicated, so you can imagine this can be a bottleneck. But for each of these particles, we need to apply the nonlinear function. There's no assumption here of anything, right? It's going to be an assumption on how this distribution is if you follow first-order methods. But it could be any other thing, any other function that you can imagine, that you have already a distribution. So in this case, you are not limited for Gaussians here. So then you do this m times, you propagate this, and that's it, right? So then you will have a new set of samples that it's going to be, I don't know, something like this, right? Basically, yes, on average, you will be moving, well, not on average, but if you want to take like a constant bias, definitely the action here is going to affect a lot how all this particle moves, right? And well, this is going to be the particle set after executing an action. This is equivalent, that's what I'm writing it here, this is equivalent to having belief to xt from 0 to t. Okay, so maybe you are asking, what happens with the previous particles? Why are you not doing anything with them? So they simply stay there, right? Let's say that we keep them in memory, and then we are going to have like this for xt minus 1. Here we have this for xt minus 2, right? This xt minus 3. We have this, but since there's no new action, and this is a filtering scheme, we are not going to change these particle sets. So in practice, although this belief is from 0 to t, all these previous ones have already been estimated because of Markovian and properties and causality. That's also important. You are not going to change this estimation, right? Future observations and future states will not be affecting you. It will not change this state. And basically, you have all these particles, but you only care about the last part of it, right? The one that is relevant. That is t minus 1 or t. Okay, so after doing this, then we are going to have like our new distribution after executing the action, right? Similar as we had on the propagation step. Any question here? So imagine you have this on your problem set 2. You need to execute like what is the prediction step. Do you have like a clear idea of how to do this? No? Yes? Okay, maybe you will see. Yeah, you have a strong yes there. It's going to be this, just a big 4 with all your particles and then drawing some samples in whatever noise here you are considering. But, okay. So nothing new. Here what we are saying is we have this previous set of particles, wherever this comes from, we are just adding a little noise, right? See, it's not really big, and then we have still our set of particles after this propagation. Now, for the next step, I need to introduce like a new concept, which is called importance sampling. And actually, particle filter is based around the importance sampling part. So is anybody familiar with importance sampling? No? Yes, yes, yes. Okay. Okay, so we have some people, not all of you. So let's explain it for those of you that already know. I think this will look like a review. For others, this is a gentle introduction, so this is more of the idea, right, with some. Well, with the essentials to describe this. So imagine that we want to calculate what is the expectation, right? Here we have an indicator function of our variable to be inside a region, right? And I'm going to give later what is an example of this region, but it could be like values from 10 to 11, right? So this is our region A. And we are basically counting how many times this random variable is there, right? So this is the expectation, like how many times this actually is 1 and not 0. Okay, and for this, we basically have this function, well, whatever it is, and then here we have a distribution, right? So this is the definition of expectation, but with respect to the probability P. I'm just here emphasizing it this way, right, in case that it was not clear. So importance sampling, it's based on the next principle. We don't have access to P of X, right? This is our target distribution. We don't have access, or it's very complicated, or whatever happens. It doesn't matter. What we need is another distribution, right? Which is going to be our proposal distribution. So it's going to be this trick. How to calculate this without having access to this distribution, right? And for that, here I'm writing this, but this could be any function you want, any variable, whatever. It's simply because later the example is based on this, right? So I can write it this way, right? What I'm writing here, do all of you agree that this is equals to 1 always, right? Qx divided by Qx, this is just 1. There's nothing fancy happening here, but now what we can do is just group this into a new term, and this new term, it's going to be called our weights, right? So then we can write it this way. It's not going to be the expectation with respect to this probability P, but now of the proposal distribution Q, right? And then we have the same thing, except for a little detail, right? That this function is multiplied by this term, right? And this is what we are going to call our weight. Weights, important factors, you name it, right? So this will be like a formal definition, right, of these weights. What is exactly importance sampling doing? We just do this trick. We multiply and divide by same distribution. Nothing fancy. But then later, we are going to see the price to pay, right, which is this in the form of these weights. Okay, so then these weights are this target distribution divided by proposal distribution, and we call this importance factor. Okay, and let me then write this. So this is target distribution. Imagine you don't have access to this distribution, but still this is what you want. So you can guess that our target distribution is going to be belief, right? This is what we want. But maybe you don't have access directly to this. If you had, then we don't have a problem. It's solved. We have access to the distribution, we just sample, and that's the end of it. But in this case, target distribution in general will not be available, or it's not practical. So usually can't use. And this is proposal distribution. Okay, so I'm just defining things. P of x, Q of x, and weights. Yes, please. For any reason, I mean, that you cannot use it, it could be for different reasons. One is you don't know it. Another reason is it's not useful. It's not going to give you, you can of course estimate it, right? Actually this can be, but again, maybe this is not the thing you want. Even if you could estimate it, you can still, you still don't want to use the target distribution, right? This is a simple trick, because for some reason, and this is still a little magical, what is this proposal distribution? Well, there's a lot of insights into this, how to come with a good proposal distribution, but for some reason, let's give this as an assumption, your target distribution is not good. You don't like it, not useful, call it. So definitely you will need like some measure of that when you calculate weights, right? So I think yes, then. Okay, so this was a little abstract. Let me just write like an example, right? Imagine that you want to calculate what is the probability of sampling, in this case, a one-dimensional random variable, one-dimensional. Well, what is the distribution of sampling from, oops, this distribution, and then basically x is in the interval, I don't know, 16, here on this example I was using 15, 17, right? In this case, this P of x, it's just going to be normal distribution, right? 0 and 1 mean. And well, you can guess that it's going to be very hard. So what we are doing on this indicator function is counting the number of times that we are in this interval, right? 15 to 17. So then you go to your Python random number generator, you start sampling, and after some millions of samples, you get tired because you don't get any match here, right? So why is that? Because this is your target distribution, right? And this is where this interval is, right? So this is actually very, very far away. It's going to be very unlikely to sample this. Does everybody agree? Or maybe you have infinite number of clusters and that's not a problem. But this is where important sampling comes from. So imagine that we have now we have another proposal distribution. And in this case, because the problem is, okay, we want to sample from this region, let's say that our sample distribution, it's going to be like this, right? You know this interval. This problem is a little trivial. But let's say that, yes, you propose this distribution. Why not? I mean, you can even propose another that is closer, or not even so likely. And then what is the good thing about this? That this interval is no longer at 15 sigma or 17 sigma of your distribution, right? This is going to be more likely to sample. You are just proposing this because at the end, this is what you want to measure. This is an example. Again, it's a little made up, but because finding the proposal distribution is usually complicated, but still, we know this, right? So then this is excellent, right? Because most of our samples are going to be here. So what is this Q of X? Well, for instance, okay? Yep. Okay, that's a good example. So let me show you what happens when you start like just estimating the weights, right? You come here, and then you start sampling, and you may get some points. So according to your, because remember that the problem here, it's counting the number of times that your sample goes here, right? And you just count 0. So basically the probability of this is 0. Because according to your samples, although you have like very, I mean, whatever nice weights you want to use, you still couldn't get any sample from your particle set to be here. So that's the problem. It's not really to have like accurate weights or not. The problem is having representative weights. And in this case, it's an indicator function. You need to count if you have like a sample here or not. Or imagine the other way around. You are very lucky. And your third sample, or let's say after 50 samples, you get like a sample here. What's going to be the probability of this? It's going to be, I don't know, 0.01. When actually it's 10 to the minus, I don't know, a lot. Right? So it's this problem. It's not really like having accurate weights. It's more like having a representative set, right? And no, by representative, what I mean is that for the given problem, in this case, it was counting the number of times that you have here a sample. There's like enough particles in your particle set that are going to give you like an answer to this. In this case, it's just counting the number of samples that are there, but it might be estimating the state. And imagine, can you estimate a state if you have 1,000,000 samples and only one of them is on a representative, let's say, area of your state space? That's usually bad, right? Why do you have 1,000,000 minus 1 samples not doing anything useful? Okay, so anyway, the trick with this is we propose a new distribution, in this case this one, and then basically what we need to do is we are just going to count the number of samples that we get from this new distribution, and then we need to correct by the new weights, right? So in this case, okay. Here on the notes, you have here a little more math, but basically your okay, probability of X being in this region, right? So this is A. Right, just gonna do the same thing, indicator. Right? So, and in this case, XM has been drawn from Q distribution. So remember, Q distribution is this. We are just mean 16, and then we are just counting how many times. So this is not really the solution of the problem, because now we need to calculate these weights, right? And then just to undo this, if you want to have the solution for this, it's going to be this. So this product of the target distribution, in this case, this is the value. This is a 0 mean covariance 1, target distribution. Imagine these things will be around 15 or 16, so this is going to be extremely low. And then here what we have is the distribution of, the target distribution, right, evaluated. And we said that it was this, right? So this is going to be a larger number, a very small number. You multiply this weight by this factor, and then you have the solution with very few samples, right? Here you don't need this to be like a super large number. You just need to do this correction properly. Okay, so does everybody agree that still, if we have like two different distributions, one of them useful, another not useful for whatever reason, you can still like use them if you apply the correct correction, right? In this case, in terms of weights. Mm-hmm.
But isn't that what we want to get? Yes, the probability of getting there is almost zero.
Yes, yes. This is true, but you are going to get the exact result. So if you start doing that approximation, it's going to be like, basically what you have is an estimator of this indicator function to be like with height variance. The result is going to change. Maybe from this particle set is 0, from the other is 0 point something, right? What you get is exact results. Why? Because when you sample with these guys here, with this proposal distribution, it's going to be very easy who is in and who is out, right? And this is going to give you a very exact solution for this particular problem, which again, it's a little made up. But it's going to give you a very exact solution, right? Because with few samples, you can still see who is in, who is out. You have basically a nice number of particles that lie in the interval and others that is out. Things will work out, right, if you just count the number of particles. And then what you have to do is just pay this little price of transforming them by this number, which is going to be very, very small, but still this is going to give you like the exact value. Right? So it's not really that you cannot do it. It simply is giving you like more proper definition of problems that with infinite samples are okay, but with limited number of samples are not possible to be solved with high accuracy, or at least I would say this is low variance, right, on your estimator. Yes, exactly. So we are going to get to that point in a minute. But that's a very relevant question. So are we using it? Have we already used this in step number 3? If you remember, oh, it's a little down. Okay.
Actually, I also have the same question about this patient filter for full states. It also doesn't seem to be used.
Full states? No, it's not. So this was just a derivation that we did. Well, first of all, the step number 3 here. Yes, indeed, we are going to show that this is a result of applying the important sampling here. So our new weight, it's going to be this one, right? I'm going to show it now or in a minute. And then the second one is we have full state. We have like this sequence of here of let's say particle sets from time 0 to time t, and they are not used. So I agree. We just needed this to obtain the base filter. But once we have the base filter, and then you come here, what I said is that previous particle sets are there, stored in memory, forgotten forever, doesn't matter. You just care about the last and most recent particle set, right? So on your estimation, it's still strictly true. You are not using, but you're estimating it. Or let's say that you estimated it before. New actions and new observations are not changing this observation because Markovian property is there, right? So it's a full state. No, it's a complete state. It just depends on well, in this case, it depends on the current previous state and actions and observations on that time step, not on the full history. So although, yes, we consider them later for when we do propagation and later on correction, you just use the last of the particle sets. right? So it was more part that we needed to do the derivation, this slight variation on the base filter. But once you have estimated them, you have your particles, you keep them stored or whatever, and then you are just be using the last one. Okay? So important sampling. Now we see like a solution for a problem that was hard. Yes. Exactly. Okay, if you don't care about exactness, so your question is basically why do we care? You just approximate this with your target distribution, you use it anyway, and this is good enough for you? This is the question. The answer is that's fine, but if you want to do proper state estimation or proper calculation of this function, you should be proposing like a target distribution that helps you get an accurate solution. It doesn't matter if it's small number, right? Maybe you need this kind of precision for whatever application you have. So if you say, yeah, it's 0, and you move away, I think you have done a poor job. Okay. So there was another question. Okay, let's move on because we still have some things to discuss. Next one is this comment on exactly, but what are we doing on the correction step, right? I think, yeah, it's an interesting one. So this is equation 3, right, in this filter. And then basically, let me rewrite this on this following way, right? So this is going to be our target distribution. This is better explained in terms of importance sampling. That's why I have just explained it. Target distribution, and we know that this is going to be equal to some likelihood of the observation, our observation model, and then our previous belief, right, from time. Okay? So in this case, this is going to be target distribution, right? This is what we want at the end, and this is going to be our proposal distribution. So I'm just obtaining this from the base filter, this variation of the base filter. So this is great because we already have a particle set, right, that is representing this distribution, this belief. So this is going to be our proposal distribution. That's one of the reasons why we cannot really sample from it, because we already have this set, right? This is the input, sometimes the input of our algorithm, and then we do some modifications. But let's assume that you don't have direct access to this. You just have the particle set, okay? And then there's other terms here multiplying, right? And at the end, what we want to get is this target distribution. So it's going to be the following problem, right? So what we are going to do is each of these particles now has like some weight. We don't know about it, but what we are going to do is calculate the right weight such that then this part here transforms this proposal distribution into our target distribution, right? So it's going to be just this reweighting on all our particle set, and then we'll get like our desired target distribution, or let's say our belief. This is what we are looking for. Okay, so xt is already drawn or sample, right? And then what we're interested, so, okay, so it's this thing, right? So each particle of xt, it's just going to be the previous one. I mean, we are not going to change particles, right? The only thing we are going to change is weights, right? And for that, let me write it this way. So we have here target distribution. This is the likelihood of the target distribution, and this is the proposal. This is same as we described before, okay? So we are here. Remember, we have this distribution with a lot of particles. We have this, which at the end, it's just a likelihood function. It's going to be saying like how likely it is given your state to have this observation, right? And then there's going to be a normalization factor. And actually, it turns out that this is going to be our weighting factor. So this, now let's see how this simplifies so much. So let's say that our target distribution, I'm just writing here the definition. It's this. I'm just putting like this for each of the particles. Right, so this is each of the particles on the belief. Right, remember it's this thing. And this target distribution is divided by our proposal distribution. In this case, what we are going to be proposing as proposal distribution, it's going to be this. I mean, no surprises, right? I already said that. That belief, it's going to be our proposal distribution, right? So at the beginning, it was a little strange why your proposal distribution is this. So we have it. That's first of all. And the second important thing is that here, there's going to be a simplification, right? So it's true. Here, we are just evaluating for each particle. This is just whatever weight it is inside each of them. And then each of them cancel out, so that means that our weights are simply this, right? Are simply, oops. And it makes sense because this is the likelihood function for each particle. Now, remember that we were doing this here. So this is from the propagation with bars, and this is the target distribution. This is the final belief. We are going to maintain the same variables that we get, but we are simply going to reweight them accordingly to this observation. Okay? And this is the likelihood function. It's basically going to be saying, if you have a particle that gives you like a high probability of observing whatever you have observed, this particle weight is going to increase. If you have a observation that it's not related to your state, it's like very unlikely to happen, this weight is going to decrease, right? So with the same particle set, you're just going to be saying regions or subsets of your particles that are likely according to this observation, right? So imagine you have your full particle set, and this function is just going to be like reweighting things. And this is going to be actually your target distribution. This is going to be our belief. So it's kind of amazing, right, how much this simplifies. You can repeat the derivations at home if you want, right? But it turns out that weights are just this, applying the likelihood function with normalization. Remember that still here you have a normalization parameter, right? So you need to make sure that this here. Okay, so I was talking about the example. I think with 2D you will see this much more clear. I'm going to write here like this is our particle set. Another amazing thing from this is that, do you remember that at the beginning I was talking about weights? So what happened with these weights? They just cancel out. It doesn't matter initial weights, right? So these weights cancel with these weights, so it doesn't matter for the propagation part what these weights are in your particle filter. It will only matter later when we apply the correction, right? And that's why we are recalculating. We are not multiplying this by this. There's not such a thing. So we have the full weight, not a multiplication to the previous weight. Right, so this is an important thing. You will see later in resampling that actually these weights are going to be like equal, but okay. So we have propagated our bunch of particles after executing some actions. Imagine it was moving to one point, right? We have this distribution, and now I'm going to define like a couple of landmarks because, okay, it's easy to give like an example that we are working on. So here we have this landmark, right? And here we have this other two landmark. According to the explanation we did in lecture 5 when we were explaining models, remember that this was like the observation of these landmarks. Basically, there was like a bearing, a range, and then some signature, right? So forget about the signature now. Okay, I'm going to put it like this. Right, we just have some range and some bearing, and basically it's something like this, right? So this is for landmark 1, this is for landmark 2, right? So we see that with this observation function, I mean with this observation that we see, that is the same for all particles. Imagine that this is R1 and this is phi1 and this the same for 2. Basically, with these observations, we know that we should be in this area, right? Whatever particle it is, we should be in this area. For instance, this particle, it's very far away. It's very unlikely that you have observed this from here, right? Because then you will have like this range and here this other range, like very, very different, right? So actually, it's going to be important here. So these weights are just going to be like small, okay? Nobody agrees that this particle should have like height weights. On the other side, these weights should be bigger, right? This should be bigger. This a little less bigger. And this is still, right? So the closer you are to what is the like the expected position, I mean the peak on this likelihood function, just based on the model that we explained the other day. You can have any other observation function, but based on this, on range and bearing that you observe, you should be kind of here, right? Because just do some simple triangulation, and this will give highest match. Okay, so then what is going to be our posterior? It's the same thing, right? But I'm just going to write like with bigger circles, like this, and then all the others are just going to be smaller, smaller to the point that we don't get even that. So this is the same this is the same particle set. I haven't changed positions of X. The only thing that I have changed is weights, right? So we are kind of reweighting them, but it's the same. Someone will ask, okay, why don't you just resample from this distribution to get like a distribution of, let's say, propagations, and then you calculate here this, because we cannot really resample things from here. We don't have access to this belief distribution. We only have the previous samples. So imagine now that this function, instead of being here, it's like somewhere else, like very, very far away. So this is the kind of observation that we get. We should be seeing something like this. And there's no particles here, right? So if we get to this point, basically we have done something incorrectly, right? This is called particle deprivation, or particle sets. It's not representing our state. And a way for avoiding this is just to do this reweighting, and then we need to make sure that with our limited set of particles, there's always going to be like someone like in the vicinity of these interesting areas, right? So this problem can arise. This is actually one of the limitations of real implementation of particle filters. And to avoid this, we are going to discuss later what is a way of solving it, which is resampling. But imagine that this is not always like this. You always end up like in positions where you have particles. If you do this many times and then you propagate these height values many times, at the end what you will get is that in these interesting regions, you might have empty set of particles that are actually weights with non-zero, right? Because you have done like multiple of them. Most of them here are with weights small, right? You do this multiple times, and then these particles become absolutely useless. And then you don't have like particles in these regions that are going to be like, so either you have much more than what you need, or you do this reweighting step, right? But this is necessary. If we don't do here important sampling, just doing the usual propagation of things, it's not going to be enough. Okay, so I hope I have convinced you that, yes, important sampling here plays this fundamental role on correction, right? Now we have this particle sets with different weights, and now the important question is, as I said, how can we use these weights on a meaningful way, right? Because remember that when we do this calculation, weights are going to go away, right? So why am I saying that we keep weights if we later just cross them? That will be not very useful, right? So actually weights have a very important function, and I'm going to explain it now. Oh, wait. Well, so if you want to write like this a little more properly, basically I'm going to write it this way. Problem. On the notes, it's explained this what I just said, but this degeneracy over time, it's basically it's this problem that we create a set of almost almost an empty set of particles, right, with weights that are non-zero. So at the end, this is going to be bad. We want to have particles here with height weights, and we want to have enough of them. Okay, so hold on. I think I did something wrong. Okay, 1 minute. Okay, let's see if it works. Maybe, Marcel, you can sit there and scroll down. Because it can only write, but it's not really doing anything else. Oh, no. Okay, let's do a short break, 3 minutes, and we'll be back. Okay, sorry for the interruption. We are ready again, hopefully, to talk about resampling, right? So this is the solution for this problem, not for all problems. Right, and the idea is very simple. So it's just survival of the fittest, right? We are going to have our particles, and we are going to let them survive depending on how much, what is the quantity of these weights, right? Okay, so how is this going to look like? We are going to have here like some particles, some of them bigger, some of them not, right? This is our initial, and then only some of them, right? At the end, we are going to have the same number of particles, right? Only some of them. So for instance, these two, but we have these two like a couple of times, and then some of them, one of them here, one of them here. Only some of them are going to be chosen. And here we have M samples randomly selected, right? And the decision for this, it's going to be proportional to the weight of each of them, right? So I think when you were asking about what is the random variable here, it's related to this, right? So you can consider also your weight to be like a random variable, and then we are going to do a selection based on that. It's not the same as the state variable, right? But this process, it's just going to penalize those that have those particles that have low weight, and it's going to reward more those that have high weight. Okay, so this is the first approach, by the way. There's a better way of doing this. But on this first approach, which is called independent resampling, what we are going to need is create a distribution on these events for selecting or not selecting a particle, right? And for this, we create a cumulative distribution. In this case, the cumulative distribution looks like this. So this is previous value, and this is the weight, right? So each of them is going to be adding like something to this cumulative, and this is going to be normalized. So for the one-dimensional example, you will have something like this, right? We start at Z0, here at 0. Then this is going to be weight 1. This is going to be weight 2. Maybe this is weight 3, right? And we basically have enough of them that are just doing this, right? So we are just accumulating these values. You sum all of them, and this should be probability 1, right? So that's why we need to normalize. So, okay, we have this cumulative new distribution on our particles. And what are we going to do? Just independently sample from this, well, let's say distribution. Okay, so here, 1. So let me write the algorithm like this. We sample M times. Here what we do is, okay, maybe not U, but A. It's this uniform distribution from 0 to 1, okay? One second. Yes, please.
Why we don't have other CI on this diagram?
Because C of 1 equals this. C of 2 equals, I mean, if you want, you can grade it. But what I'm grading here is just what is the value of, yes, this is a cumulative vector, right? So this is what I said at the beginning. We create this new distribution just with cumulative values of your weights. You have this now normalized. It has to be normalized, so it's not exactly this, but well, with some multiplication. A distribution from 0 to 1. So what you do is you sample from this uniform distribution, and then here with this random variable, you basically find the interval that belongs to this sample, right? And then you start just accumulating all these particles, right? Same as we did before. So you sample. Say that your distribution is here. So this function, what it's going to be doing is telling you to which particle this sample belongs. So in this case, it's going to be W3, or particle 3, right? In this case, it's 1. You sample m times from this, and this is just a process of selecting which is the sample that you should be selecting. You need to do this m times. This is why this is called independent sampling, resampling, right? You just go here m times, sample, see according to this distribution of importance which particles should survive, which ones should not be drawn, and then that's it. This is okay. There's a small problem with this. And let me write it now. So the problem is that over time, independent resampling induces a loss of diversity, right? So if you imagine you are sampling from this proportional to these weights, and at the end, if you do this many times, you are just going to let like those particles with high weights to survive, while others with small weights, which might be important, are very unlikely to be sampled. Right? So this can be a problem because basically the diversity of your population is going to decrease. Problem. Why is that a problem? Do you care about diversity? If you have your sample, imagine you have your optimum sample. Is not that what you want? No? Yeah. Exactly. So even if you could sample your optimal sample, this is not the ideal case. Because then when you add noise to the system, which you are going to be doing, right? Your transition function adds noise, your observation function adds noise, there's uncertainty there, then you will not adapt because you have this single sample that it's going to lay on this space of almost 0 weight, right? So basically then your population is going to be a sample, which was very good, but it's not so good anymore with a weight that it's almost 0. And then you're going to resample it because there's nothing else, right? Your cumulative distribution is going to be telling you this is the best thing you can do, but just because the diversity went down. So then it's going to be hard for your filter to recover states. You are always going to have like non-representative states. So diversity is important in particle filters. Okay, diversity of the population. Decreases over time. Okay, so again, this was just the first approach to this, just for you to get an idea on okay, we should be like doing resampling, but it's probably not this the best way, right? And actually there's an algorithm that you will be implementing, which is called the low variance sampling. that it's going to be more convenient for our problem, right? So we are going to be building a cumulative distribution as well. Okay, so this is 0, this is M2, W3, W4, 5, and 6, okay? And this goes to 1. So imagine we have this set of particles, right? We have 6 particles, each of them with these weights. Now, the idea is instead of just doing independent sampling from each of them, as we did before, we still want to preserve like this difference in the population, right? This diversity on the population. So we need to find a way still to resample on a probabilistic way, but such that we maintain this diversity, right? And then the solution, or one of the solutions to this problem, is called the low variance. So now what we are going to do is, well, I'm not going to write the idea. So we have initial random condition, and then we sample at fixed intervals, right? Or let's say that we add particles at fixed intervals. Okay, so an example of this. Imagine we have this problem, and now instead of having like this vector of the cumulative distribution, let me write it like yes. Let me write this as a circle, right? So I'm just grabbing this distribution into a circle, right? And here I'm just writing this, so this is 1. This corresponds to 2. Number 3 was big. Okay, maybe. Okay, a little, more or less, right? So we are grabbing them. And then basically what this algorithm is saying is that we have an initial condition, right? We are going to sample from a small interval that might go from here to here, right? So this is going to be D. Let's start with D equals 0, right? And then we are going to have like equal selection of samples, right? So in this case, we want to maintain 6 samples. I'm going to do, well, actually, this might be different than in your notes. Yeah, you see, I'm inducing error. Life is like that. Okay, so what is the result of this? Our prior particle set consisted of particles 1, 2, 3, 4, 5, and 6. This new particle set, I'm just going to here write the indexes, right? It's going to be with this little increment. This is going to be a random variable later, but we start with this. This is going to be what? This belongs to particle 1. So we are going to have 1 here. This also belongs to particle 1. This belongs to particle 3, 3 and 3. And then we have a last one, which is 6. Okay? So this is the procedure for selecting this. Now, if we add like little noise to this, imagine in this initial condition, so the initial condition is bounded. I'm going to plot it this way. This. It's going to be the same. So we have an initial condition, and then what we do is we add 1 divided by the interval that we want to sum, right? So in this case, for this D equal, I don't know, D1, this particle set, now it's going to be a little different, right? So the randomness comes on the initial condition. So imagine, you can imagine, this is kind of a shifting wheel that you have, and then all these intervals are always the same. This is 1 divided by m. It's simply changing the initial condition. So why is the reason for that? The reason is that with this heuristic, we can maintain diversity very easily, right? So there's like a preservation, or if you want, like, yeah, preservation on the space, right? So if you have like this probability to be large, this means that most likely, yes, it's going to be like samples drawn from here, but still there's some variations depending on the initial conditions. And for these regions where you have like small particles, or you can still get samples from this, right? If you were like doing independent sampling, and most likely the solution is going to be this big region, right? All the time sample, right? Almost half of it, right? So this is not what you want. This will be this loss of diversity. You want to maintain these little ones, these little weights on particles. So in this other example, can you help me here? Which particles we should be including? This one is 1, okay. This one, 2, okay. Now things are changing a little, right? But still it's very similar, so you see this, and here we are just adding 1 by divided by m, right? Here now it's going to be, yes, again 3, here we have another 3, but here we have 4 now. So it's one of these minorities. 5 is lost, it's fine because it was not representative, but we are not losing all of them. And here again 6, right? So these are 2 examples of how to sample, right, from this cumulative distribution. This has like a little better properties. And then one of them is that, yes. D is sample from a uniform distribution from 0 to k, and k is value to be seen. Usually, k should be smaller to the interval, right? So this is your initial condition. You're just going to be sampled once, right? You have this initial condition, and then you keep adding 1 divided by m. So let me write now the algorithm. Low variance, right? What we need is the initial set. By the way, if you want more explanations on this, prop 110, right? In this, well, it will be explained a little how this process is done, so you might see like more material. But I think the idea is, well, the idea is what we explained here. Okay, so you will get simply a different point of view, probably on a different format, but it's still useful. So if you want, take a look at the book. Yeah, please. No, I didn't say that we have an unbiased estimate. I mean, if you see, this algorithm is called low variance, right? So here what we are looking for is a resampling algorithm that is low variance, right? Height variance will be the independence resampling strategy. It's not an estimator, it's a resampling strategy. And height variance in the sense that then your diversity gets reduced, right? With this low variance, I think you are also preserving like variance in your estimator of the particle set, right? With respect to having other algorithms like our independent sampler. So we are getting simply a different set of particles, but this in particular has this property. So our particle set is going to be low variance with respect to an optimum, if there was an optimum. I mean, if you knew the information, if you knew the perfect estimation of your state variable, of your distribution of fixed t, imagine you have the perfect function for that, this will be low variance with respect to that. So your estimator over multiple different tries of sampling and different initial conditions will have low variance. Okay, so we'll see. Basically, yeah, I said instead of d, let's call this function r. I don't know why I wrote this. And it's going to be sampled from this initial interval from 0 to M. And then basically we have here like this iteration or this loop, right? And then basically here we have a value that this is this initial one. Okay, if you want, you just find you find the interval that belongs to this, right? And here what we are doing is adding constant intervals, right? And then our particle filter, our particle set, it's just going to be this union, right, of new and this is an interesting part, right? So the weights, it's going to be equally probable, right? So new weights on this resampling strategy have like, well, equal weights, which is a nice property that we want, right? We have seen that having height weights sometimes might be bad, especially because maybe other non-relevant particles can still be useful later for unexpected observations. But we also discussed that these weights are just going to be changed after we go on the likelihood function. And then, yes, we just return xt. Okay. Yeah. Yes, so the initial conditions for this algorithm are, yes, we have an xt that is empty. Okay. Okay, so this is all. This is all we wanted to discuss today. Now, you've seen that these 4 lines or 5 lines that we describe on the particle filter, we have actually derived them. We have now discussed what is this resampling strategy, right? So problem set 2, it's going to be about implementing this. You will see this in action. You will see every part of the formula that you need, right? So that's a good practice, I believe. Now, how to apply this? So this is also, well, particle filter, let's say that it's an algorithm for state estimation, but in the particular case of localization, this is called Monte-Carlo Localization. There's a folder in Canvas on readings. So you can take a look at this work by Dellarts and others from '99. And it's basically explaining this, right? So how to use particle filters into the problem of localization. Okay, so basically the algorithm is not changing much, is what we have explained before. First, we do the sample of motion model, and then we do this reweighting. And finally, we do resampling. You do this iteratively, and this is the first approach to the Monte-Carlo localization. There's a little variant. If you want to take a look at the probabilistic robotics book, that's also possible, right? So there they explain like a little variant just to preserve this diversity. But now I think we have discussed everything that is related to particle filters and Monte-Carlo localization, and you are ready to implement problem set 2 or use particle filters anywhere that you need like these non-parametric distributions, and this is important, your dimensionality of your state variables is not very large, right? If it's large, this doesn't work very well because, you know, the number of samples depends exponentially with the dimensionality. So for localization on 2D, it's fine. For other kind of problems, might not be that well. But still, this is still used nowadays, this localization algorithm. Okay, so next lecture, we are going to be talking about SLAM. You can take a look at probabilistic robotics, chapter 10, and then I'm going to also add like, now I'm going to start adding more files to the Canvas. So it's not just the chapters in probabilistic robotics, but maybe some specialized publication, right, explaining like a particular thing. So you might also take a look before coming here to class. Okay, thank you very much. See you tomorrow.